This job so far getting people back, so I assume that means everybody's stimulated and has lots to talk about, so that's good. Our next speaker is Tom Phillips, Altair Professor of Physics at Caltech and Director of CSO. Tom has his early degrees and PhD from Oxford, but after spending a little time there, he went to Stanford in the US, then to Bell Telephone Labs. He tells me at Bell Telephones it was having arguments with Arno Penzias about the performance of millimeter and submillimeter receivers that finally drew him into the field of radio astronomy. So Bell Telephone Labs scores indirectly again in having another one of the great players in the field of radio astronomy. Tom then went on to Caltech, where he's been for the last 30 years, and an enormously illustrious career related to the development of millimeter and submillimeter amplifying devices. And as a result, it will be delightful to hear Tom tell us firsthand about the way some of these were invented, SIS, HEB receivers, but also the way they are transforming space telescopes like Herschel through its HIFI instrument and the ALMA millimeter array. So Tom, over to you.
Well, thank you very much, Ron, for that very thorough introduction. I'd like to wish Rad many happy returns on his 1000th moon. I must say a moon is a much more poetic unit than a year. I think we should all switch to moons. I've worked for many years now in the Caltech Submillimeter Observatory, and I'm going to tell you how I got there. And I know this talk's supposed to be about radicals, and you might think that some of my efforts were radical, you might not, I'll let you judge. But the first effort, I can say I wasn't at all radical. I just didn't know where, in terms of thinking outside the box, I didn't know where the box was. Ron was correct to say that Arno Penzias influenced me a lot in terms of radio astronomy. I was trained as a low-temperature physicist, so I arrived at Bell Labs knowing a lot about low-temperature physics and nothing at all about radio astronomy. And Arno came and gave a talk in which he had announced the detection of CO and explained how it was all possible due to the excellent receivers he was able to build with noise temperatures of about 20,000 Kelvin, which seems very high today, but in those days that was a big... in fact, he had any receiver at all at 115 gigahertz, which was the CO frequency, was remarkable. But being somewhat naive and somewhat obnoxious as a young person, I asked why it was 20,000 Kelvin and why it wasn't 5 Kelvin, because 5 Kelvin was the number that was in my mind for translating in quantum sense the noise from 115 gigahertz, which is about 5 Kelvin. So Arno didn't like that at all, and he got hold of me afterwards and said I could either shut up or go away and build a 5 Kelvin receiver. Of course, I chose the latter, and it didn't come out at 1,000 Kelvin. It came out about 100, but it was a lot better than 10 to the 4. But it has other problems, as I'll explain. The first detector that I tried to build was called a Hot Electron Barometer, and that was a very simple system, which was just a little rod of indium antimonide supported across the waveguide in the E field, where it was matched to the waveguide fairly well and produced a very bolometer-like result. That is, a bolometer can be a mixer detector because it's a square law detector. Anything that's a power detector is a square law detector, which means that it will be able to mix the electric fields of the signal on the local oscillator. So the device was very simple. In fact, the same device works all the way from about 100 gigahertz up to about 600 gigahertz. And we found this out gradually, step by step, and it therefore was solely responsible for raising the frequency availability for radio astronomy, for spectroscopy, from 100 to 600 gigahertz, or a factor of 6, which is a remarkable step for a simple instrument. So that's what it did. This is the circuit it was put in, and you can see there are actually two detectors here, with a magic T, which was just explained as an invention of Dickey, here, and so the signal comes in, gets split, and then there's a second oscillator here, providing the mixers for the 150 megahertz IF. Well, at least that's the carrier for the IF. The IF is a problem with it turned out for this receiver because it's only a megahertz. That's to say that when the electrons in the bolometer get hot, they travel around and are scattered in terms of ionized impurity scattering or Rutherford scattering. And at low temperatures, the hot electrons pass more easily past the ionized impurity and therefore have a lower resistance. So the resistance is a function of the heat, which is a function of the input photons. So that's how the bolometer works. But the IF is only about 1 or 2 megahertz at the most. So this was a problem, but I didn't realize it was a problem because, as I said, I didn't know where the box was. However, we used this receiver for several years. We used it to detect CO2 to 1 for the first time. And that was an amazing week. We spent it on the Kitt Peak 11-meter telescope, and hadn't managed to get the receiver to work all the way up until the last night, and then it started to work, and then it was raining, and we thought we'll have one last look, but we couldn't look through the front of the dome because there were metal bars across the front. We had to look through the side of the canvas dome in the pouring rain, and we looked at Orion, and there was this huge strong line which we were able to calibrate. So it was seen in the pouring rain in the somewhat difficult circumstances. Now, actually, when we calibrated that frequency, the line, it turned out to be about 75 Kelvin antenna temperature. And the 1 to 0 line, which had been detected by Arno and Bob and Keith Jeffords, was at 36 Kelvin. So it looked, at first sight, as if it was an optically thin line, because it increased in antenna temperature as you went up in frequency. However, by the time we got back to Bell Labs from Kitt Peak, there had been a recalibration of the 1 to 0 line, and that was also 76 Kelvin. So the line went from being optically thin to optically thick in one evening. And of course we pushed on at various times to all the other lines of the CO ladder, 2 to 1, 3 to 2, 4 to 3, and then got to the atomic carbon line at 492 gigahertz. Now, you wouldn't expect to see, or at least we didn't at that time expect to see atomic carbon in the interstellar medium in the molecular phase, because it was supposed to be molecular. And so we searched for atomic carbon, and let's see. Oh, this is just the 2-to-1 receiver, which I explained. This is the Earth's transparency. This is from a high mountain site like Mauna Kea, and there's good transparency apart from a few water and oxygen lines up to about 400 odd gigahertz. And then there are two more windows at about 700 and 900, 800 gigahertz. And this is the spectrum from an airplane, and that is how we worked for the 492 gigahertz line detection here. You can see there is a nice gap here at 492, although the rest of it is very blacked out, and this is what Sophia will see when it gets going. This is the detection of 3-to-2 CO line, which is myself, somewhat younger there, and Patrick Huggins, who was my postdoc. We're standing in the prime focus cage of the 200-inch, and this is the receiver mounted at the prime focus of the 200-inch. This was the coldest night of my life. Optical astronomers don't have it easy, I can tell you. They used to sit in the prime focus cage all night, absolutely freezing to death, and not able to move because it would jog the guiding. So that was a really cold exercise, and I sympathize now with optical astronomers. Okay, so here is the Kuiper Airborne Observatory, the inside of it, and that again is Chaz Weissman, Jocelyn Keane, and myself. Here is the receiver mounted on the receiver plate of the Kuiper Airborne Observatory. The telescope here is only 91.5 centimeters. You have to include the 1.5 because it's very small, and it's a big fraction. The telescope therefore has a fairly big beam at 492 gigahertz, over a minute and a half roughly. And that's interesting because the atomic carbon in the interstellar medium turns out to be very widely distributed, like CO. And so the detection of it was made easier by the fact that it was bigger than the beam, whereas most of the molecules in the interstellar medium are centered on the Orion source and don't extend very far, so they don't show up much with a big beam. So it was a bit lucky that the beam was big and which matched the atomic carbon. We had a long battle thereafter with the theorists who didn't want to believe that there was atomic carbon in the interstellar medium, or at least not in this particular part of it. Okay, this is the spectrum that we would have hoped to get from a very wideband spectrometer of high resolution. There would have been a lot of high density molecules in the high density region here, in which we now call the line forest, and then there would be lines like CO or the others not put in, and then lots of hydrides taking over at short wavelengths, and this was our hope, that we would be able to see this spectrum. We realized after a while that we couldn't do it from the ground or from airplanes. We would have to do this from space, and so we've been trying very hard to get a space program going, and as you heard from Ron, the Herschel program is now going extremely well, and I'll explain how we got into that in a moment. So this was my second attempt at a receiver. It became clear that the indium antimonide hot electron barometer was not adequate for general purpose use. In other words, no one else liked it, just our own receiver. A general purpose receiver, though, had to be built. And so I had the idea that it would be a good thing to have an analog to the optical photoconductor, which has, where there's a band gap in a semiconductor material of about 0.6 volts for silicon, say, and this would be an analog in the submillimeter band with something with a gap of a few millivolts, which is the milli-electron volts are the units for the submillimeter. That is therefore the only thing with such a gap is the superconductor, and so this obviously had to be a superconducting detector in some way. Now, there was an experiment that had been done at Bell Labs earlier by Ollie Dahem and Martin, which was called we call photon-assisted tunneling, and that is a tunneling process. Here is the superconductor with a tunneling allowed from this side to this side if the electrons, if the pairs can get broken and one of the electrons can get up high enough to go over to the other side in a tunneling process. Okay, this is going to be the local oscillator frequency, and you can see that they would break pairs at the surface here, and they would go up individually. The electrons would then be able to tunnel over, and you can see this process happening in the IV characteristics. Here is the current with no local oscillator power applied, and it goes along until the bias changes enough that these levels become equal, so that these electrons here can transfer over to here directly. That's this point here, the so-called gap frequency, 2 delta over E. So that's the passive characteristic. If you apply local oscillator fields, say at this frequency, then at a lower voltage of bias, there will be propagation of electrons across the gap and a tunneling current. And that is this step here. The tunneling current sets in here. And so there is a quantum mixing possible between the local oscillator and any signal field. So with this detector coming along in 1979, I moved at that same year to Caltech, and I immediately, thinking that I was going to be able to build the Caltech submillimeter observatory, which is what I thought I'd been hired to do. However, what happened to me was that the division chairman said there's a problem with NSF. We've got a personality problem between Alan Moffat, who's the director of the Owens Valley, and the NSF, and they're going to shut us down if we don't get this thing built, and you have got to take over, pointing at me, and build this thing. Not so easy, and it became a little difficult to find out how I could do the job. I was helped a lot by a remark from Rad at that time, who was visiting, I think, who said the director does not have to be the smartest person. This enabled me to take the job. Because Alan Moffat was undoubtedly extremely smart. So, after 3 years of effort, we got it built. And there it is as I left it in the early 1980s. So, the first experiment that we did on the first antenna in Owens Valley was a line survey, and this absolutely took our breath away when we saw what we got. This is the SIS receiver working very well. They're the standard receivers now in radio astronomy in this frequency range. And this is a spectrum from about 200 gigahertz to about 270 gigahertz. And it's just got lines everywhere. There are little bands of lines. There are SO2 lines. There are methanol lines. There are just and CO lines. Just lines everywhere. This spectrum was Jeff Blake's thesis, and it was a very important result for the Owens Valley and for our efforts for higher frequencies. It was also an interesting mathematical exercise because it was taken double sideband, which means that you get all the lines on top of each other from the other sideband in a survey of this kind. And we found a method for getting the thing back, decomposed, back to single sideband, which this spectrum is single sideband. It's an analog of the clean technology in radio astronomy. And this is actually a maximum entropy plot, in fact not quite clean. Okay, so then having got the Owens Valley organized, I was allowed to go off and build the Caltech submillimeter observatory. And here is Bob Layton, who built the telescope. Actually, Bob had an argument with the NSF too, because he had written a proposal to build 4 telescopes, 3 in the Owens Valley and 1 on a high mountain. But the proposal hadn't been fully funded by the NSF, who had said he could only build 3, the Owens Valley 3, and then reapply for the 4th. He didn't see it that way. He saw it as having to build 4 for the price of 3, which he did. And that was a good thing because it put us well ahead of the game. So in 1984, when the money finally came through from the NSF to build it, we'd already built it. So we only had to bring it over there and assemble it. This is Bob hammering in a stake, which is going to be the center of the CSO site. And here is the telescope, 10.4 meters, very accurate, about 13 or 14 microns at its best. And you can see some of the other telescopes in the background, and not the Keck observatories or Subaru, which haven't been built yet at this time. So this was a very neat dome design, which goes around with the telescope. It's slave to the telescope, and that saves us a lot of room. And we have rooms in the back there to control everything. So this is an example of a modern receiver, which has, in this case, 2 SIS receivers, one for the reference input, one for the signal. So it looks at an off-axis point, as well as the on-axis point, and so one can take the difference immediately. It also has 2 magnets to suppress the Josephson current, and it's what we call a correlating receiver. It turns out that if you're building receivers and you've only got 1 receiver element per pixel, you haven't really finished the job. You might think you have, but you haven't. It turns out that you can have 2 for 2 polarizations, 2 for image sideband suppression, 2 for 2 for bounce input, and 2 for on-off positions on the sky. So actually you can put, if you really want to, you can put 16 elements on one pixel. And I wish somebody would design a system that would do that, because the signal to noise would go up a lot. Now, you remember I said earlier when we wanted to get the full spectrum of the sub-millimeter, rather like we were able to see just the 70 gigahertz at the bottom end in Jeff Blake's thesis. Well, this is Herschel, which is a European Space Agency project. It has 3 receivers on it, or 3 systems, instruments. There's PAX, which is a short wavelength spectrometer and low resolution spectrometer. SPIRE, which is a intermediate wavelength instrument, and HIFI, which is the heterodyne instrument. Now, this came about, it came about that the US was involved in this because we had started pushing for a sub-millimeter telescope in space in 1980, or actually 1979. And we got it into the field committee report as one large project to be built, but we never really got the budget through the NSF and NASA. And up to 1985 we had money for it, but in 1985 there was the Challenger accident, and everything that was scheduled to go on the shuttle was kicked off, and we were told to redesign for a Delta rocket, and we did that. And so we went from a large unknown diameter but a deployable system, probably around 10 meters, down to about 2.5 meters on the Delta. And we was at the head of the queue of the Explorer line, but nevertheless behind Sophia for many years, until I realized we were not going to get there that way. And so Genzel and I wrote a paper indicating why it would be good for NASA to join up with the European Space Agency to get this job done. And neither ESA or NASA liked that, but they nevertheless went along with it. And so this is the result. This is a European Space Agency project with NASA as a minor partner, but actually having paid $200 million for our contribution. So there's a very powerful heterodyne instrument on here. It's called HIFI, and it has 14 bands between 500 gigahertz and 1900 gigahertz, which is pretty high for a local oscillator system. And it's remarkable. It had one accident at the beginning where it was hit by a cosmic ray, which knocked it out for a while. But it's back in business, and it's getting beautiful results. I'll show you some of them. This is a piece of the spectrum of one band of HIFI. I'm not allowed to tell you which band, and it hasn't got frequency markers on the bottom. It's one of those things that's embargoed. But if you knew what you were doing, you could find out where the frequencies, the line frequencies were. So this is the kind of data that's coming down, and it's really beautiful. Now, this is something that I really like myself, which is a spectrum of hydrogen fluoride, J equals 1 to 0. That is the line which may be one of the most prolific or ubiquitous lines in radio astronomy. It is in black, and this is the continuum. Here's 0, here's the continuum, and then there's an absorption feature here. This is in W49, down to 0, and then several more down to 0. And you can see the other spectrum is the para water ground state line, 000 to 111. And that is about the same for this piece of the spectrum, but in other cases it's not as deep in tau as the black spectrum, which is the hydrogen fluoride. So hydrogen fluoride, in spite of the fact that there's not much fluorine, is in fact doing a better job of absorbing the continuum than water. So water was always thought to be the basic coolant for molecular clouds, and here it is being beaten out by hydrogen fluoride. We haven't got all the data in on hydrogen fluoride yet. We've only been going about 6 months, and we haven't had all the time. Three instruments share that time, but the hydrogen fluoride is really terrific, and I think it's going to be useful for distant galaxies because anything you can see the continuum in, you're going to be able to see this absorption feature and measure its Z value. Here is W51, which is a similar situation. The hydrogen fluoride being stronger, even though it's 10 to the minus 4 of the oxygen abundance, fluorine abundance, nevertheless is more effective in absorbing. This is because it's such a strong bond. The hydrogen, if the basic frequency here is 1232 gigahertz, so that is really high frequency for a 1 to 0 transition. So that shows you how strong the bond is. It's a very short bond. Now, the other place where these SIS receivers are being used is in ALMA. And luckily I don't have to build them all, but there are 60 telescopes in ALMA and about 5 bands, I think, frequency bands, so that would be 300 receivers someone has to build. And they're doing very well at it. Here is, I think the system has 6 telescopes at the moment. This is just an artist's impression. But it is beginning to take data now, and they have very good receivers, probably almost quantum noise limited. So they won't have to be replaced by better ones. There can't be better ones than quantum noise limited. So we're very happy about ALMA, we're very happy about Herschel, HIFI, and just very happy. Thanks.
Okay, well, thank you very much, Tom. Open for discussion. Bernie?
I'm not surprised that the HF is stronger in absorption than water. The water has a huge partition function that knocks down the population, and HF has a much larger dipole moment.
Yeah, but these are absorption spectra, so everything's in the ground state.
Everything. Oh, are you guaranteed? That is, these regions are so cold that there are no molecules in the higher states?
These are very high frequency transitions.
Yeah.
So, and the water's not very different in its frequency from the HF. So they're all down in the ground state, sitting there waiting for a photon to absorb.
So the partition function has nothing to do with it?
Not in this case.
So it's just the dipole moment?
Yeah.
Yeah.
Tom, you mentioned that when NASA joined Herschel project, neither ESA or NASA liked the idea, but do you want to enlarge on that? So how did you manage it?
Well, it was 1990 was the year, and Charlie Towns was running a meeting in Liège, and Gensel and I were going to it, and we decided that there were 150 people present, that we would get them all to sign up to this motion to join up the two groups. And everybody did, everybody signed, and Charlie was happy and confirmed that it should be done. And we sent this result to NASA headquarters and ESA headquarters to get back very angry letters on how it wasn't our business to do that, and they would decide if they wanted to do that, and so on. But nevertheless, you know, the staff turns over in NASA headquarters fairly fast. And we soon found somebody who thought it was maybe not such a bad idea after all. And they did get together and do very well up to a point. And that point was when NASA, which had been given the task of making the telescope, suddenly decided it wasn't going to do it. And it pulled out. Just one day simply said, no, we're not going to do it. And this infuriated ESA, but actually was for the good, because it was made out of silicon boride. Anyway, it was a material that was extremely good and has been shown to be very effective for telescopes. And it was a big step forward that the Europeans actually built a better telescope than we could have.
Thank you. Okay, thank you very much.